Okay, I wanted to talk about logs because I thought they were crazy. And the reason why is because, I should have known this a while back, but I think I'm finally beginning to grok it. So I just wanted to just talk about it because I thought it was really exciting. So, why use logs, right? We tend to think of so log base 2 of something equals something. Okay, this is bad because n. Okay, so why is this important, right? So x is going to be equal to this, right? How many times can we raise 2 to get n? So if x, if x is 100. Okay, maybe a bad example. Let's say x is 8, right? How do we get up to that? It would be 2 times 2, right? Times 2. So we raise 2 3 times to get 8. Simple enough, right? So why is this really important? Well, I was reading about heaps, right? Just to read about it, really refresh my memory. If you remember what a heap is basically an implementation of a priority queue. Big words, I know. But anyway, we have a binary tree, right? And by definition, a binary tree has a node and at least two children, right? This guy has two kids. Now, usually in a binary, sorry, a heap, we're dealing with a complete tree. Complete tree meaning we have all of the levels filled out, and if they're not filled out, then we still have nodes filled out on the left side, leftmost, right? So why is this important? Because heap guarantees us several things, right? First is that we can always pop out the first element, and it's going to be guaranteed to be either the smallest or biggest, right? I'll get to the log thing again. But also we could pop something out from, sorry, no, we're not going to pop this out. We would pop out the top element, the root, right? But we could also add something to the tree. So we could add something here, right? Now the cool thing is that pop and push, right, respectively, these over here, they're log operations, log n operations. Why? If we think about why, it's quite interesting because the number of comparisons, let's write this down, number of comparisons is going to be the log n of the size of the tree. Why is that? So depending on the size of the tree, we're going to know the number of comparisons. And easy enough, right? When you think of log n operations, it's like, okay, all we're really saying is that we're splitting the search tree by half, right? So like if we're looking on this side, it's like, screw this side. We don't care about it. We're just going to care about this side. So in effect, we reduce half of the search universe, right? We don't need all that. But this is really cool to calculate because if we know the number of nodes, let's say, I'm going to remove this for simplicity. But let's say we pop this out, right? Then we would move 7 over to here, actually, and this would become 1. And then we would percolate down to make sure that we maintain the heap variant that what's at the root is the smallest. So 2 should go up, right? So how many comparisons are we doing? Well, there's 7 nodes, right? So what's log 2 of 7? Well, 2 we can raise 2. We can't raise it 3 times, right? Because that'd be 8. So it'd be like 2 something, right? But we'd raise it up. So it'd be 3. So at most, we're doing 3 comparisons. One's at the root. Then we split it. We have 2 choices now. Make one more decision. Then boom, we make one more decision, one more comparison. So if we know the number of nodes that we have, then we can determine how many comparisons that we could do. Now, I will finish this video by just demonstrating how efficient logarithm operations are, because logarithm grows very slowly. What do I mean by that? Log of base 2 of, let's say, 15 is what? Well, 2 to the 3, would it be 4? Because 2, what's my exponential? 2 to the 4 is 16, right? So it'd be 2 to the 3 something. So let's round it up to 4. That's 4. Log of, so that's 15 elements we're going through, right? Log of 1 trillion, okay? 1 trillion is a million millions. So that's literally 12 zeros. Still short. Okay, I think this is a 1 million mark. Am I right here? 3, 6, 9, 12. I think this is right. A million millions. Yes, 1 trillion. The base 2 logarithm of 1 trillion is just 40. So we went from 15 elements to 1 trillion. But this is only 10 times greater. 40 operations on 1 trillion. That's nuts. Geeking out. Peace.